You know the states of matter: solid, liquid, gas, depending upon how much you've studied physics. Yeah, there's plasmas, Bose-Einstein condensates, liquid crystals, all sorts of other things. They're not in this course. So what's a fluid? Well, the defining characteristic of a fluid is that it flows. So it's not a solid. So a liquid is a fluid, and a gas is a fluid. A lot of those other esoteric things are too. In comparison, a solid, rigid body moves or deforms as a whole body, barring fracture. So a rigid solid isn't a fluid. Granular solids are sort of, though. You can pour rice or sand. Some materials can also be in the gray zone. Think of silly putty or cornstarch mixed with water, which are kind of solid-like, and call it kind of fluid-like. Once again, in this course, we'll focus on simple liquids and gases only. So, like a solid, fluids obey all of the same laws of, all of the same fundamental laws of physics. The things that you've been learning for the last several years, things like conservation of mass, things like conservation of energy, things like conservation of momentum. They also follow E and M and all sorts of other fundamental laws of physics, but what we'll use in this course is quite a lot is conservation of mass, conservation of energy, and conservation of momentum. So far so good, but unlike a solid, fluids respond to stresses very differently. Fluids respond to stresses by flowing rather than deforming. So instead of a discrete amount of shear strain in a solid, there's a shear strain rate in fluids. Instead of the amount of normal extension in a solid, there's a rate of extension in a fluid. So when you apply a load to a solid like this one, it deforms to a point where the internal stresses balance the load applied. And when you remove that load, the solid returns, at least partially, at least mostly, to its original shape. Now, on the other hand, for something like a fluid, here we've got a fluid trapped between two cylinders. Somebody's rotating the inner cylinder. And as that happens, the fluid starts to shear. The fluid starts to flow. And it's never going to deform enough to hold back that inner cylinder. It's just going to keep going as long as you're applying that load. Even once the person stops spinning that inner cylinder, the fluid keeps flowing for a time until viscosity slows it down. And once that's done, every bit of that fluid does not, unwind backwards and come back to its original location. So the definition in words of what makes something a fluid is that fluids are material, are substances that can't withstand an unbalanced shear stress without flowing. If you want to think about it mathematically, they have no shear modulus. But why do fluids flow? Well, it's because the intermolecular forces are too low to prevent it. Think back to thermo or materials courses. Solids have strong intermolecular forces. They're strong enough that they can keep it in a crystalline structure or an amorphous structure or a polymeric structure, whatever. The intermolecular forces are strong enough that they keep all of the molecules together. If you think about liquids, well, those materials, you've added enough energy that while the spacing hasn't changed much, and while there still are some intermolecular forces, the liquid molecules can flow around each other. The intermolecular forces are not strong enough to keep them locked together. If you think about gases, well, those are much more broadly spaced and there's much faster because you've added that much more energy in, and so they're just zipping around with almost no intermolecular forces. It's important to remember, though, that while we're talking about molecules here, that's not how we deal with things in solids or fluids, and that's because of the continuum approximation. So what that means is that we're assuming there are enough molecules in the volume that we're considering that we can ignore the molecules and just treat it as a homogeneous chunk, a homogeneous continuum. So if you think of a cube that is 1 micrometer on a side, how many molecules of air do you think there would be in that? So air at standard temperature and pressure, in that 1 micrometer cube, there are 27 million molecules. And if that's not crazy enough to think about, it's 99% empty space. So those molecules are zipping around so fast and are so tiny and are so spread out that they have almost no molecular bonds, but they're also bouncing off each other so often and so frequently. And so we'll come back to this because this idea of these intermolecular forces are what give us all of the fluid properties that we use in fluid mechanics, also what gave you all of your properties in solids and thermodynamics. So we'll come back to it, but that's just to give you an idea of why is it that fluids flow. To think about fluids mathematically, we're going to have things like velocity, acceleration, stuff like that. So take a pen or your phone, throw it from one hand to the other. That chunk of matter just traveled through space as one piece. In contrast, we have to think about a fluid as a collection of chunks of matter because each one of them can flow and interact with each other. So we call each one of these chunks of fluid a fluid parcel, short form FP. And a fluid parcel is a chunk of fluid that's small enough to move together or to stay together as one piece. So small enough to move together as one piece, small enough to do calculus on once we're really doing math with it. And regardless though, once we've got a fluid parcel, there's two ways we can think about the velocity of a fluid. So a fluid parcel's velocity is, just as usual, the time rate of change of position. So it's the rate of change of position with respect to time. So it's the usual definition. Velocity, units of meters per second or length per time, is the rate of change of x position, y position, and z position. It's a 3-component vector. All of the things you've learned from dynamics already. So if we track fluid parcels this way, individually, then we're thinking of them in what's called the Lagrangian perspective. And that's what you've been doing in dynamics all this time. You just never called it that because you haven't needed to. This is a useful perspective. It helps us think about how different chunks of fluid are going to feel as they flow through a flow field differently. It's also helpful if we want to know, for example, where a particular pollutant that was released at a specific time has traveled since then, because we're going to track it until it goes to wherever we want. To picture the Lagrangian viewpoint in fluids, picture standing on a bridge over a creek or a stream. Let your eyes track a leaf as it's flowing down the stream. That's the Lagrangian perspective. You're tracking the leaf, the specific bits of water that's carrying it. It's being pushed by the fluid parcels and solid bodies around it. It's also pushing on them as it flows. We don't usually track each individual fluid parcel. There's a lot of them. Mathematically, it becomes way too complex to do. So especially when we're thinking about the math of fluids, we don't think about tracking individual fluid parcels. Another reason why we typically don't think about individual fluid parcels is they tend to leave the area of interest. That particular leaf just floated away. You're still on the bridge. And if you care about the forces on the bridge, you care about all of the fluid, not just the bit that just left. So we're often more curious about the effects of the flow or the effects on the flow, the force on the wing, the erosion of the stream's bank, the effect of the compressor on the fluid inside it, etc. So instead, we consider what's called the Eulerian perspective, which introduces the need to use a velocity field. So the velocity field is the vector field that describes velocity at every point in the flow for every instant in time t. So velocity field is the velocity v of the fluid parcel at x, y, z at the instant t. So very similar definition. It's still dx dt, which we shorthand as u, and dy dt, which we shorthand as v, and dz dt, which we shorthand as w. But all of them depend upon position. To picture the Eulerian perspective, imagine that same bridge and that same stream. But this time unfocus your gaze and look at the whole stream. Down here, there's a little tiny swirling eddy behind the column of the bridge. Over there, the water's curving around the bend formed by the bank. You see blades of grass being bent over as they're growing in the shallows. You're looking at the current time t velocity at each point and seeing how in different parts of that stream the water is flowing differently, flowing in different directions, flowing at different speeds. Fluid mechanicians have to be able to switch from Eulerian to Lagrangian and back and forth. We will talk about both in this course because you need to think about both to really understand how a fluid is flowing. There are times when it's easy to interchange them. There are times when it takes more work. We'll talk about some of the mathematical ways to do it when we need to. Finally, as a note, in advanced solid mechanics analysis, you also deal with vector fields. If you're talking about the full deformation of a solid body, you are considering the deformations as they vary in x, y, and z, and the deformations in the x, y, and z direction. So you can break things down in the exact same way for high-level solid mechanics as well. So hopefully some of the stuff that we're teaching you here will help those of you who are really more into solids.